Hello! Now that we have learned how to measure an error, we are ready to do something cool. In this video, you will see how to apply the simplest form of learning to create a quote-unquote neural network that actually learns. It will be able to update its own weights in order to extract information from data and figure out how to make better predictions. To be honest, calling it a neural network is a bit of a stretch. It is going to be just one neuron. It will have one input, one weight, and one output. And it will not use the algorithm that professional neural networks use. We will start with a very simple example that we will improve upon later. It will be an important building block that we can learn from and use to build up to more interesting and realistic examples. The algorithm we will use is called hot and cold method. It is called this way because we will try to tweak weights in two different directions. We will simply increase the weight a little bit and see if this improves our predictions. Then we will decrease the weight a little bit and see if that improves our predictions. And then we will compare the errors between two weight values. And as a result, we will be able to choose which one of the weight values results in better predictions. That will be our optimal weight that we will use to make better predictions in the future. We will do this step by step. Instead of increasing or decreasing weights by a large amount, we will have a tiny step size that will be just a number, so-called learning rate. And it is going to be used to update weights little by little, step by step. And every time we update our weights, our network will be able to make better and better predictions. So without further ado, it's time to get started and look at the code, and everything I'm talking about will make a lot more sense. So to begin with, I'm going to copy a little bit of code from previous video. Again, we are going to have inputs, randomly selected weights, and the target prediction we want to be able to predict. We will also have our INN, the prediction function that simply multiplies inputs by weights. Remember, we only have one of those, so we don't need any of the fancy matrix multiplications for now. And we will calculate the prediction and the error right away. Just to avoid wasting any time. Like so. Finally, we will print out the results for future reference. Print prediction will be this, and error will output our error. Let's see what we have. Right now we have a pretty tiny prediction. Let's do a little bit of better formatting. So we have a very tiny prediction, 0.8, which is nowhere close to what we actually want, 0.7. And we have a pretty big error, relatively. Because we have a lot of numbers over here, I will apply round function. I know it's not something you want to use a lot in practice, but for now it will be much neater if we will have prettier numbers. So I will wrap prediction in round. And I wanted to round it to 4 decimal points. Same thing with error. Round. Now it will have only 4 digits after a decimal point, just for our convenience and for pretty printing. Great. The next step is to try to tweak weights a little bit. We will take this weight, we will try increasing it a little bit, and see how well it predicts the target prediction. Is it getting closer? Is it getting farther away from it? Then we will try decreasing it, and also look at the results. So first, let's make a prediction of up variable, up, that will contain the prediction with a little bit of higher weight. Again, we will use our INN function. It will accept inputs as always, but instead of a weight, it will accept weight plus what? It's an interesting thing that we need to figure out here, because by how much are we going to update our weight? There is actually no hard and fast rule for figuring out by how much you are going to update your weights, but we will set a variable called learning rate, and we will set it to something small, let's say 0.5. This variable means that we will update the weights by this much. If we want to update weights faster, we will take this number, we will set this number to be higher. If we want to update weights slower, we will set this number to be lower. You will see in the future why it matters and how to set it better, but for now we will just use our intuition and assume that this is about the step size that we want. So let's add learning rate to it. And now we are able to make a prediction that is based on the weights modified by this learning rate. And once again, we will calculate our error. I will just copy paste the code. So it's again going to be error up based on the modified weights. It will use prediction up, see how close it is to target prediction, and square it. And here we will again print out the error. Except this, in this case we will use prediction up and error up as well. Excellent. So what do we see here? We used to have a prediction of 0.8, now we have a prediction of 0.9. We want the target prediction to be 0.7. So what we know is that our prediction moves in the right direction, so it's a little bit higher, it is a little bit closer to 0.7, but it is still nowhere close. So we might need to repeat the step multiple times, and that will result in improving our predictions and getting closer to the truth. And error here is 0.37, which is lower than 0.38 that we used to have. So it looks like increasing our weights by a little bit improves our prediction. But we had no idea of knowing about this, and it might as well have made it worse. So we also want to check what happens if we decrease our weights by a little bit, and then we will compare the results. Because sometimes it might be possible that a decreasing weight is what leads to better prediction, and increasing weights worsens it. So we will do the exact same thing. Actually, you know what, I will not even type it, I will copy and paste this code. Except I'm going to switch the plus sign to the minus sign. It's going to decrease our weights a little bit, and instead of up, I will replace it with down. Prediction down. We'll calculate error down, taking into account the prediction down. We will replace it here as well. And let's modify our print statements to see exactly which one is what. So this will be for prediction up and error up. And same here. Down, down. So what are the results? Well, when we have decreased our weights, very predictably, as you have probably guessed, our prediction became worse. It got farther from 0.7. It got lower, and our error instead increased because now our prediction is farther away from our target. So clearly, if we update our weights a little bit up, our prediction will improve. I hope this is clear so far. And let's write a little bit of logic that will do this for us. It will see which of the predictions is better based on which of the error is lower, and then it will update the weights accordingly. So let's compare the errors, which, as you remember, is a standby for the quality of our predictions. Error up, error down. So if the error up is higher, that means that our prediction with increased weights is worse because the error is higher. And if it's lower, then it's better because the error is closer to 0. So in case increasing our weights results in worse predictions, we are going to decrease our weights instead. So we will move them in the opposite direction. Weights, we will simply subtract the learning rate from them, so that we make this change in the variable permanent. And of course, if instead our error up is less than error down, then this is exactly what we want. That means that this first case worked out just fine. We have improved our weights, our error has decreased, and this is the update that we want. That means weights, that means we will want to add learning rate to the weights. So this is the thing that we want to happen instead of this one. Great, adding learning rate. And now our weights variable updated, and if we will see the outcome again, so if we'll try to use our regular prediction and see how well it predicts, it outputs exactly this first case output. So we have updated our weights to increase them, and now we are a little bit closer to the truth. Excellent. But as you can see, we are nowhere near close enough. So what would we do? Well, in deep learning we have something called epochs, and they are just iterations of this learning process. So what we have seen so far is just one step of a learning process, and in order to get closer and closer to our goal, we will just repeat it multiple times. So we will write a simple for loop for I in range. So we will tell neural network to repeat it multiple times, in this case 100. Again, we are going to calculate our prediction. I will again just copy and paste code here. And we will measure our results. Then I'm going to calculate prediction up and see if this improves the results. So then I will calculate prediction down and see if that improves the results. So we will just tweak our weights a little bit, and then we will finally compare the results, like so. And we will update it the way we want to. But of course we don't want to do it forever, so when our prediction gets closer and closer to the truth, let's just write if error is more than 0, we want to update our weights, and if error will ever equal to 0, we don't want to update them. Okay, so now this part of the code runs, and we see our weights beginning to update step by step. Let's analyze the measurements that we have here. As we can see, prediction gets higher and higher and higher and higher every step, gradually moving forward towards eventually reaching 0.7. And error, on the other hand, as we get closer to our goal, error goes from 0.37 to 0.16 to 0.09, and to finally as close to 0 as we can get. As you can see, our error decreases and our prediction gets closer to the one we want, and tada, our neural network is learning. Look at that. We gave it input data, we gave it the target prediction that we wanted to be able to predict, and it has figured out the weights on its own. And in the future, as we will write more and more advanced neural networks, they will be faster, they will be better, but the fundamental idea will be the same. We will keep iterating through data points, updating our weights, until they result in accurate predictions. But with the algorithm that we have right now, we have several problems that will prevent us from using it in actual practical deep learning. First of all, the problem is that it's inefficient. As you can see, we have to make 1, 2, 3 predictions. And imagine making predictions with a huge neural network that has a lot of neurons and a lot of weights, and it will have to run through all of the matrix multiplication and all of the difficult computation many times. So it will have to make 3 predictions for each of the weights, and it will have to do it maybe hundreds of thousands of times. So the problem with this is that it's extremely and horribly inefficient, and unfortunately it will prevent us from using the simple algorithm. But we will use another different but still simple formula. It will involve some of the math magic that will simplify everything and make it much faster, but that's going to come around in the future videos. Another problem is if you analyze the final print statements. At first we will see that we're getting closer and closer to the truth, but then look at that. At some point in the learning process we have reached prediction of around 0.7 and error pretty close to 0. It wasn't actually 0 because we have rounded it down, but it was tiny. But then the prediction got a little bit worse, it overshot. So as you can imagine, our algorithm has decided to increase the weights one more time, because the error wasn't 0, and it saw that our prediction was too high, so it has updated weights once again and switched back to 0.7. It will be much easier to see if we will increase the learning rate to something like 0.3, because that is going to make our step size a lot larger. Let's see what happens. First of all, the predictions will increase much faster, so instead of way down the line, we reach somewhere around 0.7 in the maybe 10 or 15 iterations. But unfortunately, first it overshoots and predicts a value that is too high. Then it realizes that, oh no, now the prediction is too high and now I need to make it a little bit lower. It tweaks the weight down, but because it decreases it by too much, it decreases it and makes it way too low. And now it thinks that, oh no, the prediction is too low and I need to increase it again to make it a little bit higher. And it wobbles back and forth, back and forth. At first it's too low, and then it switches to making it a little bit higher, and then it realizes it's too high and switches it to lower, and it never ends. So as we can see, we jump around the ideal prediction, but we never reach it. We never reach the error of 0. So that is the problem that this algorithm has. Because we know the direction in which we want to modify our weights, but we don't know the amount we want to modify them by. It's not smart enough to understand that once we are close enough to our goal, we actually need to make tiny tweaks that don't overshoot or undershoot our prediction. On the other hand, if we will make the learning rate too tiny, like so, let's run through everything again. And now it will get progressively closer and closer and closer and closer, but unfortunately the learning will be happening way too slow. So after 100 iterations we all have only reached 0.1. If we would run maybe 1000 iterations, it would gradually get closer to the result that we want. But unfortunately, oh, you see, even that isn't enough. What if you do it 10,000 times? As you can imagine, a learning rate that is too low is going to take a lot more time to train. But on the other hand, it is going to get to the target prediction much closer. So as you can see, it still wobbles around 0.7, but instead of switching between 6.8 and 7.4, it's switching between 0.7 and 0.7002. So it's much closer to the truth that we want. So these are the two problems, and you will encounter a learning rate in the future, and you will learn how to tweak it better. But these are the problems that we have with this algorithm. It's inefficient. Too tiny learning rate will result in learning that is too slow, and the learning rate that's too high will result in wobbling around the prediction but never reaching the accurate one, because our algorithm doesn't understand the amount by which we want to change the weight. It only understands the direction up or down. It doesn't know by how much. And in the future videos, we will learn how to make an algorithm that is much more efficient, and it will be able to figure out both directions and the amount by which we want to change our weights. So, I hope this video was useful to you, and I'll see you in my future tutorials.